Okay, so it's a great pleasure to have Ho Yiu Chung today from the University of Southampton. And he's going to tell us about Bieberbach group and decomposing flat manifolds.
All right, thank you for the introduction. All right, so this is basically what I'm doing for my whole PhD, the whole 3 years for my PhD. So basically I'm working with the Bieberbach groups, and since it's algebraic groups that related closely to the flat manifold, so a lot of differential manifold type of question can be translated into algebraic question by studying of Bieberbach groups. So my talk is basically divided into two parts. First, I would introduce what Bieberbach group is and some famous formula to understand its structure. And the second part, we'll talk about how to decompose a flat manifold. Basically, the aim is to try to decompose it into a flat torus and a flat manifold. Decomposing it this way, it depends on how big your flat torus can be. All right, so let's begin with just the definition of the Bieberbach groups. All right, so Bieberbach, first we need to understand what's isometry. Basically, isometry is an invertible map from Rn to Rn such that it preserves the distance. And it's easy to check that it will satisfy all the axiom of being a map with respect to the composition of maps. And we just denote all the set of all isometry to be these symbols. All right, and it's a quite easy lemma that you can prove is if F is an isometry of Rn, then there will exist a matrix from the orthogonal groups and an element inside Rn such that the mapping is just multiplied by the orthogonal matrix and plus the element inside Rn. And therefore, we can express this group of all isometry as a semi-direct product with On with orthogonal group and the Rn space. And basically, it's just the group operation that we can get by using this lemma, and the inverse is given by this formula. All right, yeah. If I let gamma, which is the uppercase a and lowercase a, which a is inside the orthogonal group and the smaller case a is inside the Rn, is elements at Rn, be an arbitrary elements, then instead of you express it as a semi-direct product with the orthogonal group and the Rn space, we can express it as an n+1 times n+1 matrix in this way, in which case we basically define inclusion from this group of all isometry into general linear group of n+1 degree. And therefore, we can consider the set of isometry as a topological group with the topology induced from R with n+1 to the squared degree. And therefore, we can now describe what is discreteness of the group, etc., and compactness. Okay, so for the definition of crystallographic groups, if gamma is a subgroup of the isometry groups, we call it a crystallographic groups. If it's a discrete subgroup and the set of the orbits is compact. So since we already understand how to consider the group as a topological group, so the discreteness is well defined, and we call it the n-dimensional Bieberbach groups if it's a torsion-free crystallographic groups. All right, and then it's just a simple lemma to say that if the group is a subgroup of the isometry group and it is a discrete subgroup, if and only if it's acting properly discontinuously on Rn, So it gives you a way to determine whether a subgroup is a crystallographic groups, or instead is a way to determine whether a group is a discrete subgroups. So it's a quick example. In this case, I denote the group in a matrix notation as which here we denote it as a matrix notation. So it's easy for computations. In this case, the group is generated by these two matrix. And if you think it's a two-dimensional crystallographic groups, and if you think of a XY axis, the orthogonal matrix, which is identity matrix in here. So basically the action of the group on the R2 space, which will not have an orthogonal action. So it will not turn the object, it will just translate it from one unit to right and one unit up and down. Yep. So it's clear that it is a discrete subgroup because you're just moving a block one left or one left, one right, or one up and one down. And the quotient is indeed compact because R2 quotient of Z2 is basically a torus. All right. So it's basically a definition of Bieberbach groups. And now we move on to the Bieberbach theorems, which basically we have three Bieberbach theorems which state the algebraic structure of Bieberbach groups. All right. The first one we call the first Bieberbach theorem is proved by Bieberbach in 1911. It says that if gamma is an n-dimensional crystallographic groups, then the set of all translation, which means is the element inside the group such that the matrix element that correspond to the orthogonal groups is identity, is isomorphic to Zn. And it is the maximum abelian normal subgroup with finite index. All right. So what does it mean? It's important because it means several things. First, we know that since it's isomorphic to Zn and it's normal subgroup with finite index, so we can express the Bieberbach group, a crystallographic groups into short exact sequence as a group extension, with Zn as a quotient, R as the Zn with the kernel, G as the quotient, and G is a finite group, and Zn will be the maximum normal subgroups. All right, since we have a short exact sequence, so there's a few things that we can work on. First, we notice that it will induce a faithful representation, the row from G to L, the general linear group of degree n in this formula. It is faithful because the Zn is a maximum subgroup, and we call the group G to be the holonomic group of the gamma, and that representation will be the holonomic representation of gamma. So it's pretty useful when you are given a Bieberbach groups, then you can write in a short exact sequence, then you can have a lot of computation that you can do. Because it's a short exact sequence, so it's pretty common for us to use second cohomology to describe the extension and maybe have some homological modular homomorphism to map it from exact sequence to give some certain of calculations. All right, now from this guy, my English bad, I don't know how to pronounce this name, but from this guy from 1948, he proved basically an inverse statement of the first Bieberbach theorems. It's proof that a group is an n-dimensional crystallographic groups if it has a normal phi abelian subgroup Zn of finite index, and which is a maximum abelian subgroup of gamma. So what is said is we can make a definition for crystallographic group in this way. So if gamma is a group that fit into this exact sequence with Zn as kernel, a finite group here, then gamma will be an n-dimensional crystallographic groups. So there's a way to define a crystallographic group as well. But it's important that we have a remark. If we are given such an exact sequence without any others information, we do not know that whether G is acting faithfully on Zn. We don't know whether G is acting faithfully on Zn. So in this case, we cannot assure what is the holonomic group of gamma. What we can say is the holonomic group of gamma is a subgroup of G, but it's not necessarily isomorphic to G. So that's a thing that we may need to pay attention to when we have exact sequence, and we cannot just assume the action is faithful. All right. And then we move on to second and third Bieberbach groups. Or for the second and third Bieberbach groups, they both proved by Bieberbach in 1912. And for the second Bieberbach groups, it say that for any natural numbers n, there's only finitely many isomorphism class of n-dimensional crystallographic groups. And for the third one, is saying that if two crystallographic groups are isomorphic, then you will exist an element inside the GLN real semi-product with the Rn. Sometimes we call it affine groups, such that when you conjugate the gamma 2 with alpha, you get back alpha 1. All right. Since we already know that the crystallographic group can express as a short exact sequence. So for the second and third Bieberbach group, we just need to prove that there's finitely many finite group acting. The group action is you have finitely many choice of the action, and prove that the second cohomology group is finite. Then we can prove that there's only finitely many isomorphism class. All right. And that's a table to show that it's pretty much impossible to calculate every crystallographic groups using hand or even computers, because the cohomology group grows so fast, which we cannot even compute it up to. I think for GAP, which I'm using, I can use it to calculate up to 7-dimensional crystallographic groups, but beyond that, I think it's pretty hard for a computer to classify all the crystallographic groups. All right. Yeah, and that's pretty much. So after the Bieberbach theorem, we should know that how the algebraic expression for crystallographic group is, and because the exact sequence thing, we can know how to construct a crystallographic group by just a finite group acting on a lattice. And then when you get the extension, then you can get a crystallographic groups. All right, now, in this section, I'm trying to say there's a relation between Bieberbach groups and the flat manifold. So there's a lot of question around flat manifold. For example, what we talk about is how to decompose flat manifold, but there's a few more, for example, where the finite group can act freely on such a manifold, then we can translate that question into algebraic side by studying Bieberbach groups. All right, so that's theorem by Killing, proved by in 1891, which say that if M is a complete connected compact flat Riemannian manifold, then it will isomorphic to Rn with the gamma acting on Rn, where gamma is the fundamental group of M, and gamma will be discrete and torsion-free. So what we get immediately as a corollary is if you have a compact, complete, connected, flat Riemannian manifold, we need to be compact because as the definition for the crystallograph for the Bieberbach group, the quotient needs to be compact. And then the fundamental group is the Bieberbach groups. So there's a connection between flat manifold and Bieberbach groups. All right, then it's just a quick slide on how you translate the language of the algebraic version of the Bieberbach group, the geometric version of Bieberbach groups. So for the first one, when you remember, you can write down the crystallographic group in a short exact sequence. It's basically meaning when you have a flat Riemannian manifold, then the flat torus is a finite Riemannian cover of that manifold. And for the second one, basically we just, as the algebraic side, we say there's only finitely many isomorphic crystallographic groups. And for the geometric side, it's basically that you have finitely many flat manifold up to equivalence. And for the third one, is say that if you have two manifold, which their fundamental group is isomorphic, if and only if they are finitely equivalent. It's basically just translating algebraic version into a geometric version. All right, yeah, and then we move on to the flat to how to decompose a flat manifold right now. All right, so first we need to understand what's the Factorial extension. All right, first, let M be a compact flat manifold with a fundamental group gamma. So just record gamma is a Bieberbach group in this case. And we let Tk will be a flat torus where the gamma is acting on the Tk via isometries. And then we can construct a space M tilde across Tk, which gamma is acting on it diagonally. So what I mean is when you have G acting on MF, you just E equals to G add on M and G add on F. So it add diagonally. And M tilde is the universal coupling of the space M. All right. And then we can form a base of orbits by quotienting out the gamma, which will have the flat Riemannian structure on it. And we'll call it a flat toral extension of the manifold M. So roughly, yeah, I put down on the remark. So first remark that I'm going to make is for conventional reason, we take a point as a zero-dimensional torus. Therefore, we can say that every flat manifold will be a flat toral extension of itself. And the second one is what we actually doing is basically putting a flat manifold and a flat torus together, gluing it together to get a new manifold with dimension in sum of the previous two. It's a way to get a new manifold. And explicitly just a fiber bundle over flat manifold over torus as a fiber. All right. So the problem I'm working on is when you're given us such a manifold, how can you express it as a flat torus, extension of a flat torus and a smaller compact manifold to get the group that you're working on? So we try to decompose it into a flat torus and a smaller compact manifold. All right, next page. All right. Now we're going to talk about the Vaquers invariance. All right. It's a theorem introduced by Vaquers in 1970. Okay. Let G be a finite group, and there will exist a natural number we call NG, which is minimal with the property that if gamma is a Bieberbach group, with the holonomic group is isomorphic to G, then the lattice will contain a normal subgroup N such that the quotient is still a Bieberbach group, but of dimension at most Ng. So we need to take the minimal, because if you take Ng to be a super large number, then the statement is always it always satisfies the statement. So we need to take the minimal number. And the natural number Ng we'll call the Vaquers invariance for the finite group G. And such a variance has an equivalent geometric way to describe it. In the same paper, he translates that theorem into a geometric way by saying that if M is a compact flat manifold with fundamental group gamma, and then the translation group or the lattice subgroup will contain a normal subgroup N such that the quotient is torsion-free, then M will be a flat Taurus extension of some Bieberbach of some compact flat manifold with fundamental group gamma quotient of N. So we take a big manifold, and the Vaquers invariant means that how big can you quotient out by some subgroup inside your lattice to get a smaller compact manifold. All right. Yeah. But let me mention that first, because that's such an invariant is pretty hard to calculate. I think so far for the general way, there's only one paper that have mentioned the upper bound for the upper boundary for the such invariant. So it's pretty hard to calculate. All right, let's move on some. Yeah, it's kind of is a different definition, but somehow someone proved that it's just equivalent definition for the Vaquers invariance. So we say that a lattice is a G lattice. No, we say L is a G lattice if it is a G modules isomorphic to a free abelian group set N for some natural number N. So basically it's a lattice set N with a group G acting on it. And with a given G is a group and L is G lattice, then an element in the second column G groups, the G and coefficient is L, we say that is a special if its extension does define a Bieberbach groups. So as you may know, for second cohomology groups, it can classify the group extension up to isomorphism. So what we've done is, if the element does define a Bieberbach group, then we call it a special elements. All right. And then third things is we say L has property S if for any G lattice M and any special elements inside the cohomology group, second cohomology group G with coefficient M, there always exists a G homomorphism from M to L. L is the lattice with property S to L, such that the induced map from the second cohomology GM into second cohomology of GL will send the beta, the special element, to another special element, F star beta. Right, and we defined N prime G to be the minimum of rank L, where L is a G lattice with that property. And in 1997, Szymanski have proved that if G is a finite group, then the definition is the same. If you use the theorem by the Vaquers, the value that it got is the same as what we define up here. So yes, all right. So maybe a picture first. Let's see what basically it's doing. All right. So first now, L is a G lattice with property S of rank R with rank NG, and gamma is any Bieberbach group of dimension larger than NG with holonomic group G. So first, we can write down the middle exact sequence like this. Gamma here, you can write an exact sequence with set n as quotient and a finite group. Set n is the kernel, and the finite group is G. All right. Then since the G lattice L has property S, so we can there will always exist a map, say F here, which map set n into L, such that the induced map, which send the exact sequence from the middle sequence into the bottom short exact sequence, the L to gamma bar to G to 1. That was the morphism map is doing.
Sorry, can I ask something?
Yes, of course.
So the lower left square is a push out, right? That's how we are thinking, is it?
Which square? I'm sorry.
The lower left. The
this here.
Yeah.
Yes, you can think of it as a push out as well.
Okay.
Yes. Yeah, because sometimes when you have this function, this morphism F defined nicely, then gamma bar should be pretty easy to compute based on the cohomology group of this gamma. So yeah, it's just a picture on how the quotienting things work. Yeah, so what it does is, so what actually going on is the middle vertical, the sequence of the middle vertical thing here. You're quotienting out a lattice inside the translation subgroups, and you get a new Bieberbach groups with smaller dimension. That is the main purpose of this Vaquers invariant thing. All right, and yeah, and I'm trying to basically introduce all the result about the value that we can get about the Vaquers invariance.
Oh, sorry, could you go back to the previous slide?
Yes, sure.
Could you remind the definition of NG here? How is it related to, so the group G is the one that we are starting from, that's the finite group, right? And
yes,
you define
G is the finite group.
G, yeah, how is gamma and G are related here?
All right, first we have the Bieberbach group gamma here, and we know the holonomic group of gamma is G. Then we try to work out NG is a value where you can ensure you to have found a lattice such that after the quotienting, you get a Bieberbach group with dimension less than or equals to NG. So basically,
Okay,
we try to quotient.
So was the Bieberbach condition that was it the condition that the representation, holonomic representation, is supposed to be faithful? Is that the condition? The Bieberbach?
For the horizontal second column, the horizontal one, I assume G is acting faithfully on set n. All right, but after you quotienting out a sublattice, after you quotienting out this sublattice, we do not have any information on whether G is acting faithfully on L. So we may get a smaller Bieberbach group, but also the holonomic group might be a subgroup of that G as well. So we do not have information on that. We do not have control on whether we will change the holonomic group or not. All right. Does that answer your questions?
Yes. Okay. Thank you.
All right. All right. Let's move on. All right. Now we're going to, what do we know about the value of that invariant? So that theorem is by Cliff and Vaquers from 1989. So let G be a group, and this chi will be the set of conjugacy class of cyclic subgroup of prime order P. And what that they prove is the G lattice, which is the direct sum of the induced module from C to G of Z, has that property S. So what does it mean? Let me go back to a previous slide. So what it means is whatever exact sequence you have, you can always map into this L can always be that complex G modules. That's what the theorem says. So as a immediate corollary is we already know the upper bound for such an NG, which is by calculating the rank of this G lattice. And I believe there's a name for that G lattice. It might call the permutation lattice, something like that, but it's not important. The important thing is we get the upper bound for such NG. And in the same paper, they prove that NG is exactly equals to that number if G is a P groups. All right. So I think it's worth mentioning how to get the theorem about the P group. So first we prove that for the first theorem, we prove that such G lattice have property S. So we can always map. Let me go back here. You can always map to such complex G lattice. And if we want to prove that that is exactly the value for Gn, we need to find a gamma bar such that you cannot keep quotienting out anything to get a smaller Bieberbach groups, because after you quotienting, you may get a crystallographic group with some torsion. They try to come up with an example which you cannot quotient out anything at all to get this exact value. All right, and then we move on to things that I work on in the past 1 or 2 years for the diagonal Vaquers invariants. So first, let me introduce what's a diagonal type. All right, let's gamma be a n-dimensional crystallographic groups and rho be holonomic representation. Then we say that gamma is a crystallographic group of diagonal type if the image of the representation is diagonal matrix. All right. So it is a lemma that I came up last year. It's basically saying that, what's that? All right. We're saying that if you have a Bieberbach group of diagonal type where this omega is the cohomology class correspond to the standard extension with the set n as the kernel and finite group G as the quotient. And if you have a G homomorphism set n to m such that the f star omega, f star is the induced cohomology map, is special, then this f star omega will define a Bieberbach group of diagonal type. Yeah, maybe unclear what's going on. Maybe let's go back to the picture and be more clear. All right, so basically what I'm saying is, if this gamma is a Bieberbach group of diagonal type, I want to make sure if there's such a map F here, I want to make sure this gamma bar will be a Bieber group of diagonal type as well. That's what I meant. So the proof is not hard. Basically, we just need to consider how G is acting on this L. It's just, I think it's, as I remember, it's just a restriction of action. All right. Since we know after quotienting, you will still get a Bieber group of diagonal type, then we can define the diagonal Vaquers invariant now. All right. Let G be an abelian, elementary abelian two groups. Then we define the diagonal Vaquers invariant to be the smallest integer with the property that if gamma is a Bieber group of diagonal type with holonomic group G, then lattice subgroup will contain a normal subgroup N such that the quotient is a Bieber group of diagonal type with at least at most N subscript D G, and we call that to be the diagonal Vaquers invariant. First, we know such invariant exists because of the theorem by Vaquers. Such invariant will exist, but since we're only considering Bieber group of diagonal type in this scenario, so the invariant that we got here will be much smaller compared to the general Vaquers invariants. All right, and we let gamma to be a Bieber group of diagonal type as an immediate consequences of being acting diagonally. We know that the holonomic group of gamma need to be isomorphic to product of C2. And we let omega be the cohomology class defining the standard short exact sequence. Since it's acting diagonally, we can write the second cohomology class into a direct product of cohomology class, where all the mi's are isomorphic to Z. And the action, because we're doing cohomology class, so we always have an action from C to K acting on this M1 up to Mn, and in this group, we always have an action from C to K acting on M1, etc. So we just extend the sequence, we extend action to R because Mi is Z. So we extend the action to R. Oh, sorry. And then we will obtain the following short exact sequence here. Why we are doing that? Because we want to have such isomorphism here. And you remember the here, what we got here, we're trying to break down the large second cohomology class. And finally, what we did is we break it down into first cohomology class, a direct product of bunch of first cohomology class. And yeah, the reason why I'm going to do this is because it's a theorem from Vaquers. It says that if gamma is an n-dimensional crystallographic groups, which correspond to a cocycle alpha, what it means is the homology group of gamma is G and is n-dimensional. So, and the important part is we know that if gamma is torsion-free, which basically saying that if gamma is a Bieberbach groups, if and only if you restrict your cocycle to any cyclic subgroup of prime order, it will never be zero. So if you have a class in this big second cohomology class, after you restriction to any cyclic subgroup, we know that at least one of those class is not zero. That is the main idea how I get the the value for the diagonal Vaquers invariant, because I'm trying to figure out whether I can take away at least one. The idea for me is whether this, for example, this the first cohomology class of C2K and the coefficient R quotient of M1. My idea is whether I need to check whether I can take out this class and the remaining can still provide enough non-zero term for such class. If so, then you can quotient out, let's say, the M1, the sublattice M1, then you can still get a Bieberbach groups. That's the idea. All right, then let me bring to the theorem that me and Nansen has come up with. First is the boundary for the diagonal Vaquers invariance. It's a bit messy, but the idea is just try to considering the cohomology class. The idea is we try to construct a matrix by using the cohomology class and decide whether we can take away any sub-cohomology class. That's the idea, but it's pretty, it's not an easy proof though. All right, but for the next theorem is we found exact value for the diagonal Vaquers invariant, which in this case 1, 3, 5, and 10. It is much more easier because we already know the bound for it, and we just need to prove that, for example, for k is 2, you already know the bound is between, oh no, 2 is not a good example. I think k is 3 is a good example. When k is 3, you already know the bound is between maybe 7 or 7 to 5. Then what you need to do is you prove that for all 7-dimensional Bieberbach group of homology group of C2 to the power 3, you can always quotient out something. You can always quotient out a sublattice to get us new Bieberbach groups. Yeah, they need to consider all the cases. All right. Yeah, that's the main theorem that we got about the diagonal Vaquers invariance. And such a technique is useful because when you're dealing with different property of Bieberbach groups, there's a lot of them. For example, if you're dealing with generators of Bieberbach groups, let me go back to the picture. It's more easy when you have the picture. All right. Sometimes we're dealing with generators of Bieberbach group, which is also a conjecture stated by Decomposing and Panix in 2000, near 2000. They're saying that n-dimensional Bieberbach groups can always be generated by at most n elements. And if you know that this gamma can be quotienting our sublattice to get a smaller Bieberbach groups, then what we need to consider is the gamma prime here. We can always reduce such a question into a smaller dimensional Bieberbach groups. This technique is pretty useful when you're trying to study other property of Bieberbach groups. All right, I think it's going to my last page. All right, final, I'm trying to end my talk with an example on how such a thing does work. All right, first, we're trying to work with some 2-dimensional stuff so we can kind of visualize what's going on. All right, so for C2, first the Vaquers invariant, the diagonal Vaquers invariant is basically equals to 1. All right, and I don't know whether you remember the example that I get at the very beginning about the example of crystallographic group. Actually, it's the Bieberbach group as well. So it's this matrix, the gamma. What you do is when you have an object, the generator's element is basically you move that object 1 unit to left, right, or move it up or down. That's what this group does. All right. So when you look at the quotient subgroup, it's a torus because when you identify all the action, it will torus, and we just define the group A to be this element is basically the translation up and down. And we after we take the quotient, since we're working with the group presentation, it's pretty easy to work out what the quotient is, and it's basically equal to this one. And the important things that I want to bring up is, since gamma is the fundamental group of torus, and A and gamma quotient of A is both set. So by that we know that the torus you can view it as a circle bundle over another circle by studying how the fundamental group, aka the Bieberbach group, can be break it down into smaller pieces. That's the idea of the Vaquers construction. Yeah, that's everything. Yeah, I think I got a bit too fast, but yeah, that's everything I want to mention in this talk. Thank you very much.
Okay, thank you, Ho Yiu. Thank you very much. So, any questions for Ho Yiu?
Hi, Ho Yiu.
Hi.
I want to ask you a question.
Yeah, sure.
I'm not sure I understand correctly, but this C2 example,
Yes.
aren't you just taking a faithful action on Z, which could be just a plus minus evolution, then form a extension? Isn't it?
Yes. Right. I think that's a typo when I think I messed up two examples. I'm sorry. Okay. In this case, I think I want this C to be identity. So you do not have the holonomic group. The holonomic group is identity. All right, that's a typo. And and that exactly one example of C2 as well. If you know that's a declined bottle in two-dimensional space. When you're not when the isometry is basically when you move it, you will twist, you will flip it. So you can still quotient out a sublattice, and you still have this bundle. But when the bundle will, for torus, you just go around the circle. But for Klein bottle, you have a twist on it. So yeah.
In terms of group action, what is the Bieberbach group? The C2 extension with Z, right? Or
yes, that's also a part where after quotienting out, the holonomic group might not add faithfully on the lattice anymore, because when with the Klein bottle, you quotient out a set, what you remain is S2 as well, but the C2 will not acting faithfully on that S1.
so how do you find there's other invariants, 5 and so
You mean
NC2s? Yeah.
All right.
So is there algebraic characterization of what should be? I mean, you have upper lower bounds, but is there an algebraic way of thinking what ND is, like number of maximal subgroups so that it complement covers, like, is there a characterization of these NDs?
At the moment, we did not come up with a classification for that, for those lower bound, because the K is low enough, so we can actually make up a example which you cannot quotienting out any subletters to get a Bieberbach groups. We only can make up some examples to such that you cannot quotient. But for the upper bound, because we already have the bound for upper bound, for example, for n is 3, I think you get 3, 2, 6. You got 5 here. Oh no, that would be 4. When n is 4, you get 10. No. I'm sorry. For n is 3, you get 6 here. So what I did is I proved that for all Bieberbach group of 6-dimensional with the holonomic group is C2 to 3 copy of C2. I proved that you can always quotienting out a sublattice set such that you can still get a Bieberbach groups. which means that 6 cannot be the diagonal Vaquers invariance. That's how I push down the upper bound for specific value, for specific k. But me and Nansen cannot find a general way how to do such a thing. Yeah.
Okay, but for the ordinary Vasquez number, you don't have any theorems like the one that you have shown us for the diagonal one, right? It's, for this one, you rely on that theorem, which decomposes H2 in terms of H1s.
Yes. And for the you mean?
Yeah, that one.
You mean this? Yeah. They use different. We use different techniques because for here they prove directly how they actually construct the function f. They actually construct this function f. If you have such a lattice, they actually construct the homomorphism. And for the P group part, they really does construct a counterexample at this rank, which you cannot quotient out any sublattice. You cannot find such a map anymore. But this work way too general, and since I was working on diagonal type of crystallographic groups or Paperback groups, which have more control on the group action and more control on the second cohomology groups, because we can split the cohomology group up into small pieces, then we can have more control on how, when you're quotienting out some sublattice, what you remain and what is the quotienting, what the quotient group is. So
okay.
we give more. Yeah.
For P groups, you already know what the Vasquez number is because of this result. This NG is given by this number, right?
Say again.
For the ordinary Vasquez numbers, you already know because of
Yes.
this theorem for P groups. Okay, I see.
Yes. So for P group is but it is for general Paperback groups, but not just for diagonal. If it's a diagonal type, then this bound is not good enough because we work out a better bound for diagonal type.
Okay, I see. Thank you.
Yep.
Do you know if this NG inequality
Yes.
can be much smaller in certain non-P groups, finite groups? Do you have examples where this is much smaller?
You mean
like the inequality of that's not equality for non-P groups, right? Finite groups.
Yes, it's not equal. I think for the proof, what they did is they just found an example as the top dimension, and they just construct in a very complicated way to construct such a map, which you can keep mapping it into a lower dimensional one. So because me and my supervisor think that the way that they construct is a bit complicated and it's pretty hard to improve by just using their construction. So we are not going to improve on that way. Instead, we're trying to do the diagonal way to have more control on the action and see what we got first.
Maybe I rephrase the question. Is for finite groups, is it known if NG equals to this sum or not?
You mean whether they will be equal if G is not a P groups?
Yes.
No, it will not. It will not be equal. If it's not a P group, then you can always map it into a smaller one. I think they did mention it in the proof, but I didn't write down.
Okay.
Yeah.
Thanks.
Yeah.
Okay. Any other questions for Ho Yiu?
In the decompositions, you said you're trying to write the manifolds as products. In your examples, you had fiber bundles.
Yes.
So when do you get products? I mean, or do you always get products?
Products. Oh, you mean here?
You in the right. So you write here this as a product, not as a fiber bundle.
Yes. I think that's a more. I think this is a more general way. For the Vaquers proof, because I want to mention this because this is what Vaquers proof to prove the equivalent for the invariant, where you can translate the algebraic part into the geometric part, which they use the flat Tor extension. But for what I did, I think I do more because what I did is I try to send the strict exact sequence into a disgamma bar with a lower dimension, so it will be a fiber bundle in this case. But I did not look into how it related to the flat Tor extension. Yeah, it may be a good thing to look into after that. Yep.
Thank you.
Okay, so maybe it's time to conclude the talk. So thank you very much, Ho Yiu.
Yeah, thank you.
Yeah, so thanks.